Hi, welcome back everyone. Glad to see you once again. In the previous video, I discussed gravitational force and gravitational field intensity. And in this video, I'm going to discuss gravitational potential, potential energy, and related things. Okay, so let's start from gravitational potential. The amount of work done by the gravitational field in bringing a unit mass to a point in the field from infinity is defined as the gravitational potential. Okay, so if I consider a gravitational field due to this mass, and the gravitational potential at this point is defined as the amount of work done by the gravitational field in bringing a unit mass, that means 1 kilogram, from infinity is defined as the gravitational potential at this point. So here I draw a boundary line for infinity, but actually we know there is no boundary for infinity. Just to visualize, I just draw that. Okay, and we usually denote the gravitational potential in letter V, and if the mass of this planet is m and distance to that point from the center of this planet is simple r, so I can write an expression for the gravitational potential at this point as given by V is equal minus g m over r. So this is the expression for the gravitational potential at distance simple r from a planet of mass m. And here one thing that we are concerned about this negative sign. What is the meaning of negative sign? That's because actually we define the gravitational potential is 0 at the infinity. So according to definition, the gravitational potential is the amount of work done by the gravitational field in bringing a 1 kilogram mass. So the gravitational field loses some energy by doing some work on the mass. Therefore, the gravitational potential at any point in the field is going to be less than that of the gravitational potential at infinity. But we know the gravitational potential at infinity is defined as 0. Therefore, anywhere on the field is the gravitational potential is going to be negative value. So that's the meaning of this negative sign. Okay, and the next let's discuss the gravitational potential difference between 2 points in the field. Okay, for this I consider 2 points A and B, where A is at distance RA from the center of this planet and B is distance RB from the center of planet. So I can write the gravitational potential at A, that is VA. I can write VA is equal minus GM over RA, and similarly VB is equal minus GM over RB. And now we want to find the gravitational potential difference between these 2 points. For this I consider I move a 1 kilogram mass from B to A. So I can write the potential difference or change in potential, that is VA minus VB. That is same as referring VAB, where potential at A relative to B. Okay, so I can write VA minus VB. I can substitute these values, so I get VAB is equal minus GM over RA minus GM over RB. So here minus GM is common in both two terms. I can take that out. So I can write the potential difference between A and B as minus GM times 1 over RA minus 1 over RB. Since we know GM is equal GR squared, where R is the radius of this planet. Okay, we discussed this earlier. So R is the radius of this planet, so I can substitute GR squared in terms of instead of GM. So I get VAB is equal minus GR squared times this term 1 over RA minus 1 over RB. And here the gravitational potential difference is independent from the path. For example, if I move this mass from this way to this point from B to A, or if you move the mass in this path, still the potential difference is going to be the same. So what we can say is the potential difference is independent of the path of moving the mass. Okay, here we come to the topic gravitational potential energy. The gravitational potential energy is defined as the amount of work done by the gravitational field in bringing a mass to the point from infinity. Here the amount work done in bringing 1 kilogram mass to point P from infinity, that is the definition of the potential at this point. So I can write that is equal to V. And work done in bringing a mass to point P from infinity. So the work done in bringing 1 kilogram mass is V, then the work done in bringing m kilogram is V times m. So I can write that is equal Vm. So that is the energy associated with bringing a m mass to that point. So I can write E is equal Vm. And we know potential at this point, I can write V is equal minus Gm over R. So substituting that, I will obtain this equation. So E is equal minus Gmm over R. And also since Gm is equal Gr squared, this expression will, I can write as E is equal minus Gr squared m over R. So that is the gravitational potential energy. These terms you should keep in mind. And next thing, let's move to exchange in energy. What happens to energy if you move a mass from one point to another point in the gravitational field? For this, I consider I move a mass of simple m from B to A in this gravitational field. I can write the potential and energy at point A is VA and EA. Similarly, potential at B is VB, EB. So here EA is the energy of the mass m when is it at point A, and EB is the mass of energy of mass simple m when it is at point B. So I can write the change in energy when moving this mass from B to A, that is EA minus EB, or the energy at A related to B. So that is, I can write EA is equal VA times m and VB is equal VB times m. I can substitute that and I get delta EAB. The change in energy is equal mass times VA minus VB. This is potential difference. So therefore you can get the change in energy by simply multiplying the mass by the potential difference. If you know the potential difference between these 2 points and the magnitude of the mass, then to get the exchange in energy you have to multiply that. Okay, and I know VA and VB in terms of m and R, so I can write VA is, I can substitute those 2 terms in this equation. So I get delta EAB is equal minus GMM times 1 over RA minus 1 over RB. And similarly we know then Gm is equal Gr squared. If I substitute that, I will get this equation. And one more thing, so this is I discuss about moving the mass from B to A, that is delta EAB, and if I move the mass from A to B, that is delta EBA. So I can write a relationship between the change in energy of moving the mass from B to A and A to B, that is related with this equation. In mechanics, we use mgh as the change in gravitational potential energy. Here I am going to derive that. So here I consider a mass of m is moved from B to A. B is where a point on the Earth's surface, and A is a point h height h above from the Earth's surface. So I can write the gravitational potential energy at point B, that is EB is equal minus Gmm over R, and at point A, that is minus Gmm over R plus h. So the distance to that point is R plus h. So I can write the change in energy. So the change in energy in moving the mass from B to A, that is EA minus EB. So I can write, substitute EA and EB for this equation, then I get delta E is equal minus Gmm over R plus h minus Gmm over R. So here I can take a common term, minus Gmm is common in both terms, so I can take that out, then I get this equation. And taking a common denominator, that equation will simplify to this. And we know Gm is equal Gr squared, and very important thing, so here the radius of Earth is much larger than the height of where the mass is moved. Okay, this height is much less than compared to the radius of the Earth. For example, we know the radius of the Earth is 6,400 kilometers. Let's say for example you move this mass 1 kilometer above the Earth's surface, still that is negligible compared to the radius of the Earth. So I can write R plus H is approximately equal to R. So using these two relationship, I can yield this equation to this gr square mh over r times r. Instead of r plus h, I used r, so we get r square in denominator. So here r square cancels off, so I will get delta E is equal mgh. So this is the equation that we use in mechanics to represent the change in gravitational potential energy. And the most important thing is we can use this relationship only if the height is negligibly small compared to the radius of the earth. Okay, and then I'll discuss equipotential surface before finishing this video. So equipotential surface is a geometric surface made of joining the equal potential points in the field. Here you can see equipotential surfaces around a spherical planet. Okay, that's all for about this video. I hope I can see you all in the next video, I mean the third one. Thank you.